Good morning. Let's continue our discussion of probability, and let's start to tie probability into statistics again. So remember, statistics is the organization, collection, analysis, and interpretation of data. We've been discussing probability, and what we're focused in now is some way to make sure that we can start to bring analysis of data back into play. So today I want to talk about probability distributions. We've got a couple new formulas for that. We're already familiar with the idea that mean, which is our group average, has both a sample formula and a population formula. And of course for mean it's the same formula, but we use x bar versus mu. We're also already familiar now with standard deviation, both of samples or populations. But today I want to show you a new formula for population mean and population standard deviation that's a little different because we're living in a little different scenario. So the one we've seen before has said that mu is the sum of all the x's all over capital N, and we also said that sigma was going to be the square root of the sum of x minus mu quantity squared all divided by n. And this was going to give us our calculated process. But these more advanced formulas are not what we need if we're talking about probability distributions. And here's why. When I talk about, and I've written this very badly, when I talk about summation of x, I imagine myself having a large list of data, like we used to have. I think I usually like to have 25 things over here on the left. However, today we're talking about probability distributions. We have much less lists of data and more certain data terms and certain probabilities of how likely that certain event is to occur. So, let's take a look at our new formulas, and then I'll work through a couple of examples. Our formula is we can find the mean, remember this is population mean, by taking each of our x terms and multiplying it by how likely that is to happen. We can find standard deviation, sigma, by doing x minus mu quantity squared, sum those up for each of the different values we're interested in, and then multiply again by p of x, which we now know to be the probability of that x event occurring. And then we'll talk about these linear formulae in a second. So let's take a peek at our first example. What I have here is an actuary table. And actuary tables in general can give you any sorts of probabilities, but in common use, if you go onto Google, actuary table generally seems to talk about life expectancy. Suppose we have a company's CEO, and it's a company CEO of a very brand new company. Let's suppose that this person is 35 years old. Because it's a new company, it's a startup, we imagine that if our leader, our fearless leader dies, probably the whole company is going to be over. We don't have enough folks working in the group to be able to have some sort of succession. Actuary tables, I have picked male because males and females do have different life expectancies. Females tend to have in the United States somewhere along the order of 5 to 7 years more life expectancy, so you have to commit yourself to one or the other. These tables I grabbed from SSA.gov. However, you can find much more accurate tables that will segregate based on income, population, location, race, and other features. Health, weight, height, longevity of parents. You can add a lot more accuracy into these mix. These are rough averages for all 35-year-old males in the United States. And what we have here is a pretty gruesome table. We've got death expectancy. Because it doesn't really matter for the company as long as the CEO is alive. As long as the CEO is alive, well, life is good. Things will go on. It matters when we've got death. So our question for our company is probably something like this. What is the chance our CEO will die if our CEO does die, how much money should we bring into the mix through, let's say, insurance? So how much insurance should we buy? And our last question is, what is the expectancy of that insurance? What should that insurance cost me? And how is that all going to work out? So what should I pay? First of all, we would have to answer all sorts, and not all of these questions are as simple as I'm about to make them, so don't take this advice without at least a large, healthy helping of a grain of salt. But if our CEO is male and 35 years of age, these are the likelihood that our CEO will die. And let's say that we're thinking we're growing this company. You know, if a very large corporation, like let's say Microsoft, if the Microsoft CEO died, it would be very, very sad. But there would be people in-house who could carry on. Microsoft has tens of thousands of employees. There's people who know what to do. It's all very organized. It's only in the initial startup phase. So we're thinking for just the first 2 years, possibly, we have to do something a little bit more targeted, get some insurance maybe, because the risk of our CEO dying will completely unseat the company. So we can see the chance of the CEO dying in the first year or the second year of the company. We're hoping by year 3 that we'll have hired a vice president or something and life will be good. So then the question is, how much insurance should we buy? And that number, of course, entirely depends on the company. So for our example, I'm just going to make up a number. Let's say that we think it would cost $100,000 to be able to replace the CEO or to just pay off all the company debts and shut it down and start over. $100,000 is the magic number we picked. So the question is, now that we've decided how much insurance we need, $100K, what should we pay for that insurance? And that's going to, of course, depend a little bit as to how the insurance company wants to make their profits. So we have to think about that just a little longer. But this basic question is a probability distribution. And in particular, what we're trying to figure out is something that we call expected value. And expected value is a concept that you've already met because back in the day, we had a different name for it. We called it weighted average. And it looked exactly like this formula right here, except I don't think we called it mu at the time. Now we do, because it's a different type of mu. It's not a mu for a list of numbers, it's a mu for a list of probability-determined numbers. So expected value is all about this. In particular, we're wondering what we should pay, and I think that maybe the best way to look at what we should pay is to stop looking at it from the perspective of we're a company getting ready to pay, and instead look at it from the perspective of, let's say we're an insurance company, and we're deciding what do we want to charge these folks to insure their CEO. Because once you look at it from the side of the insurance company, then I think we get a better picture of what we're expected to pay. Because it's not just about what the total cost is, it's also about the fact that if we look at it from an insurance company perspective, we need to make a bit of profit. And we need to also cushion ourselves, possibly, from some risk. So, let's say now that we're not the small startup, we are the duck. And you are a sales agent for that duck, and that sales agent, you, has just gotten a request from a CEO saying, look, I have a small startup company, I need $100K insured in the event of my death, and I'm 35 years old, and I want to buy for a single payment from you insurance for this year and next year against me dying. As an insurance agent, here's what you're doing. You know that they want your company to pay out $100,000, and that sounds like a lot of money. So the first question is, well, what's the chance that you have to pay out that $100,000 in the first year? What's the probability of paying out that $1,000 in year 1? Well, what it is. You have $100,000. That's the amount that you might have to pay. And you multiply it by the chance that you'd actually have to pay it. In this case, 0.001631. Next, you can calculate the exact same process for the second year. The second year, if this guy didn't die in the first year, then he's managed to live to the second year, and now we have another 365 something days for this dude to die in possibly, and again it would cost us $100,000. So what you look at it is from a perspective of cost. And keep in mind, expected value is going to change depending on whose perspective you're looking at. If you're looking at it from the perspective of the company that's being insured, the startup, if I get paid $100,000 because my CEO died, sad as it is, it's still a profit. From the insurance company side, we're talking about negative numbers because if the guy dies, we have to pay the money out. So, as we're setting up this expected value problem, what we're curious about is the mu. And as we look at this mu, we're curious about, do we have to pay the 100K in the first year or do we have to pay it in the second year? So our process is exactly the same as our weighted average. We have minus 100,000 times the probability of paying out in the first year, 0.001631. Plus, because that's what capital sigma means. What's the probability in the second year and how much will we pay? Well, second year we're still going to pay $100,000. And it's going to be 0.001709. I've made a couple of assumptions in this problem, actually more than a couple, but there's a big one I'm making right now. I'm forgetting entirely any ideas of inflation or the idea that future money versus present money. We're not doing any of those complicated calculations, and they're not too bad. But for the simplicity of this problem, we're making that a little easier. Probably if I was truly giving advice to this company as to how much insurance to buy, I would probably tell them, you might consider bumping it up to 110K next year, because you're going to be a little bit larger and it's going to be a little more complicated. But let's just keep it simple. Now that we've got our numbers, it's entirely something we can plug into our calculator. So let me pull out my trusty TI-36X Pro. I've got minus 100K, and I'm going to use some parentheses. So I'm going to do parens 100, 1, 2, 3, times 0.001631. Close the parentheses, hit a plus, open parentheses, minus 100, 1, 2, 3, times 0.001709. Close those parentheses and hit enter. And maybe I should point out that when I was typing in the minus in front of here, I was not using the negative button, I was instead using the minus button right here. Alright, we've calculated this out, and I found that the expected payout for those 2 years is $334. That's the expected cost. So now, what we have to figure out, and that's from the insurance company perspective, remember, what they're saying is it's very unlikely this person's going to die. It's less than 1% both years. So it becomes very unlikely that we actually have to pay out the $100,000. Which means, if we're going to sell this company insurance, this is how much we're going to label that cost as. Yes, there's a risk we do have to pay, but there's also a very good chance that we don't. Now, of course, if you've calculated probability, which we've just done in the last section, you know that no matter what the probability says as you're getting ready to flip the coin, the fact is, as soon as you have flipped the coin, you will get either heads or tails. Which means the actual true cost, perhaps, to the insurance company is going to be either live or die, 0 or 100K. But that's not what we're talking about. We're talking about expected value. And most insurance companies rely on the fact that they have lots of people who they insure. And we know from the law of large numbers that as you get more people, the more you expect actual scenarios to work out to be according to the probabilities. So this is what it would be expected to cost the insurance company. And now, all we have to do, if we're looking at it from the perspective of the duck, is this is how much it costs me So I have to charge them at least this much. Plus I have to pay for my employee to do that. I don't know how long that takes. And I don't know how many employees this does, but they're probably going to want a couple of conversations with me. They probably want to pay by credit card, so I have a transaction fee there. So we have to add in some costs. And then, if I'm the duck, I probably have either my shareholders or I've got my company owners of some sort, and they want their profit. I don't know how much profit they have to make per person. Maybe they added $100 here. I don't know how much costs go. And in fact, no insurance company has the same cost. And so you'll notice as you shop for insurance, some companies promise you a face-to-face conversation with an agent, in which case they're going to charge you more for their costs because they have to have people. Others, promise you that you can go online and you can get it right away and that you probably won't talk as much to an agent, and maybe even your insurance card doesn't come through the mail, it comes electronically onto your phone, in which case these costs can go down. So it's all this balancing act. How much service do you think you need? Are you just buying the insurance and that's it, or do you need more of a concierge type event? But if I was going to give advice to this company as to how much they should expect to pay, I would probably be telling them, look, you're going to pay at least $334 for this because that's the cost. Plus you have to pay the costs of these folks having a company to insure you with. Plus you have to pay them for the costs of their profit. And you have to pay probably a little bit more for some regulatory fees. So I would be saying, if you can buy this insurance for, let's say, under $500, you're doing well. If you're paying $1,000 for it, maybe that's too much and you should look for a better deal. So expected value. You tend to have these probability distribution tables with certain events and certain sums. Notice despite the fact that we had the numbers 35 and 36 here, we never used those numbers. Those were not actually quantitative numbers, they were qualitative numbers, simply describing the age of our CEO and allowing us to figure out what the chance of that guy dying in those two particular times was. These probability distributions can work for quantitative data, but they very much so work for qualitative data. In particular, they tend to work for data that we call discrete. So, let's talk now that I've worked through this example, let's rewind for half a second and describe some terminology that we secretly used here. So let me pull out a different colored marker and let's take a look. These were discrete variables. And it's a feature of discrete variables. And maybe we use the word discrete in everyday language as, if I say, oh, she's discreet, I mean that she doesn't talk much. She won't, I can tell my mom secrets and she probably won't blab them out to my worst enemies. So I could say, mom's discreet. But here, discrete is meaning the sense of there's very particular categories that everything fits in. You're 35, you're 36, and for this life expectancy table, it's either or. They're mutually exclusive. So think counting stuff. How many people do I have in the room? Well, I'm going to have a whole number of people. It's never going to be 1.5 people are in the room. That doesn't make sense. So this definitely works for discrete data. We have the sense that for our probability distributions, we have what we call random variables. In this case, our variable process was all about what is the chance of this person dying. And so we're saying this person is not preordained to death or determined that they're going to live this year. There's a sense of randomness about the whole process. Features of probability distributions for this kind of thing with random variables. If your data is discrete, like it was here, we were in our first year, we were in our second year, you lived or you died. In those cases, we expect the total probability of everything to add up to 1. What does that mean? Well, it means that there's the probability of living here and the probability of dying. And the probability of dying would be 1 minus this. There's a probability of dying here and the probability of living. And the probability of living would be 1 minus the dying chance. We expect those when we have discrete situations to add up to 1. So this is a little look at expected cost. Notice that no matter how you cut it, since the total expected cost to the insurance company is $334, if you flip it in reverse and look at it from the perspective of the small startup, since they have to pay this, they're going to generally pay a sum that's bigger than this, which means when you buy insurance, you're expecting to lose money. That's how insurance works. The question you have to ask yourself is the costs part of them having a business, an insurance business, as well as their profit, is that money worth it to me in order to guarantee for myself that even if my CEO dies, this company will go on? So always insurance is a money loss process. One of the quickest examples of this that makes sense maybe is not in the case of live or die, but something much simpler. The last time I went to a nameless electronics store, they attempted to sell me a $2.17 insurance on a little power cord that I purchased for my nameless Me telephonics device that I procured. And when I bought this power cord, they offered me, it was I think $2.17 or something like that for 2 years worth of insurance. Well, they're calculating the expected probability that I'll destroy this cord. They're calculating the cost to themselves to replace the cord for me. Not at the cost of their total profits probably, but at the cost of what it actually costs them. And then they're adding in some employee costs to manage the insurance program, plus the profit their store would want to expect, because otherwise I'd go and buy a total new product there. So they're calculating that whole thing into the mix, and they're offering that to me for $2 and something cents, and that of course is definitely guaranteed to lose me money. And the question I have to ask myself is, can I afford to replace a power cord on my own and save that thing here? And the answer is probably yes. That's not very risky. Worst case scenario, life will go on. In the case of life or death insurance, the success not only of our CEO living, but of our company continuing to work and keep, let's say, 20 or 30 people employed, that's a much more responsible question with much bigger implications. And so, of course, you probably say something like, well, yeah, it's worth it to me to pay a little bit, even though I know I'm losing that money. It gets rid of risk. And that segs us nicely into this discussion about linear formulae and risk. So let me talk about these formulae. What we have is the idea that once you've calculated mu and sigma for some set of numbers, and it could be a list of numbers or it could be a probability computation, it doesn't matter. Once you've calculated those, sometimes you might like to mix them together. So what you'll see here on these two formulas is that both times what we first have is a simple formula that shows me how the two groups are playing together. This linear formula has some variables. They're getting multiplied by a number, and then we're adding a constant. This could happen if, let's say, I don't know, I decide that I want to figure out how to make a certain set of survey scores rank in terms of whether students were more or less anxious and how they did on the final exam. Well, if I have the raw score on the anxiety survey that I give, maybe students score between 0 and 10. And I find that cool as it is to score people between 0 and 10 for anxiety, the fact is, if I tell you a number between 0 and 10, that probably doesn't feel all that much to you like a score that you'd expect on a final, because a final is probably between 0 and 100%. So, instead, I take your anxiety score, and maybe I add 60 points to it and multiply by 25. So you can have a process whereby you multiply something up, so I give you a number between 1 and 10, and I tell you your score anxiety is 2. And I know that people who score a 2, those folks are very anxious, and so that makes them freak out on the final, and bad things happen. So I multiply that 2 by 20, and I get myself 40, and then I add 30 points to it, and they have only a 70. And if you manage to score a 6 on the anxiety scale, where high numbers are less anxious, maybe I multiply that by 20, and so then you can have a slightly higher number process that happens. So you can do these linear combinations. And I'll leave this example for you to work, but let me point out that if this is how you've taken your original raw data with the original raw population mean, and this is how you build your new data, then this is how you build your new mu. You don't have to recalculate all these numbers in a list and redo the summation of all those numbers divided by n. You can just multiply and add. It's a fixed transition. And sigma. Deviation behaves in a similar fashion. You take your old sigma, you multiply it by this multiplier b number, and take some square roots, and you get your new standard deviation. I'll leave that for you. What I want to work you through is one that talks about joining not a list of numbers with some constant addition, but where I take two separate lists who were operating independently and I suddenly put them together. And I want to do this in the scenario of a stock market problem, since we're still talking about some kind of company and actuary tables and CEOs. So let's take a look. Our idea in the market is that you can buy companies, and it's called buying stock. And when you buy companies' stock, you tend to find that you pay a certain price per share. And the idea is you want to buy those companies when the price per share is, let's say, $10, and then you'd like to sell it later on when the price per share perhaps is $15. However, every day, really every second during the business day, but let's pretend every day, companies are traded. And so I bought it for 10, but now we've heard some bad news about the company, and so if I want to sell today, it's only going to sell for 9. It's a bidding process, a constant bidding process. So company values go up and down. And as they go up and down, we measure not only the average value for that company over, let's say, the last year, but we also have a sense of data turbulence. And you think, I know how to measure that. That's called variance and standard deviation. And you're right. Standard deviation in the stock market is all about risk. It's about the fact that if there's more turbulence, whatever you paid for your stock might go higher or it might go lower. And that doesn't make for a very stable environment. Now, of course, we have this general sense as humans that without risk, there's reward. Excuse me, let me flip that conversation entirely on its back. Without risk, there is no reward. Because if you have the least risky stock in the world, it stays. No wiggles, but that means no additional profit for you either. So you do sometimes want risk, but it would be nice if you could be in control of your risk and decide just how much you want. Maybe it goes up, maybe it goes down, but you can control how much there is. So let's look at these two examples, and before I do that, let me point out some baseline facts about stock. Generally, you've got stock, and you can buy shares on the internet, and there's all sorts of platforms that do so. But the thing to know about stock is this: it changes. Prices, they go up or down. Entirely based on all sorts of real-world environmental facts that's beyond anybody's control. Thing two, I may or may not own stocks that I discuss. That's important too. Just because I mention some company, maybe I'm trying to shill it out to you, or maybe I'm trying to not shill it out to you. The point is you should be suspicious. Just because I mention it doesn't mean that maybe there's not some secret profit in here for me. And thirdly, I am using old data and simplified examples. These are basically disclaimers saying, please do not go out and purchase stock on the basis of one 5-minute explanation that I'm about to do. However, that being said, this is still some good groundwork to discuss. So let's now take a look at two different companies, and I've grabbed some information. Incidentally, I just grabbed these from last year's data, and I did it by weekly averages for the values. So I have two reasonably well-known companies, and I'm going to say perfectly nice things about them. I've got Oracle and General Electric, and I grabbed this data from Yahoo Finance, publicly available. Oracle gets the designation of mu1. It's the first company that I've listed here, and it had an average stock price in the last year of $33.55 per share. You could buy one share, you could buy 500. I have no idea how many you could buy at tops. General Electric, which I'm getting listed down as mu2, had a share price of $23.76. notice that you don't really care what the starting share price is. If I start at 23 or I start at 33, if this guy goes up to 43 and this guy goes up to 33, either way we made a $10 profit per share, and so probably my life's pretty good. So initial price might not be all that big of a deal. What you care about more is risk, which means you care about standard deviation. And I went ahead and calculated those already on Excel as well. Sigma 1 was 1.77, and Sigma 2 was 1.92. General Electric was just a little more volatile in the last year. We know that because Sigma 2 is bigger than Sigma 1. Again, using the methodology that I chose to calculate this. What if I could make sigma be less? Well, then I could control risk. If I wanted more risk, I would simply just buy GE, which has the highest risk. That means it has the highest chance of going up and the highest chance of going down. If I wanted less risk, I could buy all Oracle. But what if I told you that by buying both, I could cut my risk down even lower than that 1.77? That would be the power of what we call a stock portfolio. And I should warn you that portfolio theory is a huge area of research, and we're not even beginning to scratch the surface. But we have some of the initial formulas that we need to calculate this. And this doesn't just work for stocks. It works for anything. You've heard of the expression, don't put all of your eggs in one basket. Multiple baskets is the idea of portfolio theory. So we already sort of know this, but let me show you how the math of this works out. We're using the second set of things here. So I think what I'm going to do is I'm going to erase my disclaimers. And we're going to go ahead and calculate what would happen if I went ahead and bought, instead of 2 shares of GE or 2 shares of Oracle, what if I bought 1 share of one and 1 share of the other? In essence, made up my whole portfolio with half and half. Let's see what that does to our calculation. What I'm building for you is a W formula. A W formula where I have 0.5 coming from Oracle and I have 0.5 coming from GE. This isn't really my W formula anymore, is it? I'm doing a 0.5 here and 0.5 here, and I'm now giving you UW. And 0.5 from GE. So I'll take half of one and half of the other and add that together, and that would be my average price for this now hybrid portfolio that I've created. And that's not very interesting to calculate, perhaps. It's just exactly the same as the original formula. You just plug in 0.5s there. But let's see what happens to my risk. Remember, risk was 1.77 here. It was 1.92 here. Let's see what happens to the combined risk once I bought 1 share of one and 1 share to the other, and I'm now holding those combined in my portfolio. Well, we're going to have to follow this sigma W calculation, which says this. I take how much in my first group I'm taking. I'm taking half from Oracle. I'm squaring that. And I multiply that by the standard deviation of Oracle squared, which is its variance, 1.77 squared. Plus, again, I grab the amount of GE stock I'm picking, 0.5, square that, times how much its deviation was, 1.92, and square that. We have about 15,000 kids walking outside, so if you're hearing something, that's who they are. They're here for some experience the dream thing, and they're probably thinking I'm the weirdest person ever because I'm talking to myself. They can't see you, you're behind my door. Anyway, this is my sigma W. And as we do this process, we're able to see how we would join it and calculate the new sigma of the portfolio. Let's go ahead and do that. I am going to use my calculator, and let me just show you how we're pulling that off. I'm going to hit second, and I'm going to hit the square root formula. And then I'm going to hit parens, I'm going to hit 0.5 in the squared button, times 1.77. and the square button. And then I'm going to close those parens and hit plus. And I'm going to open the parens, and again I'm going to hit 0.5 squared times 1.92. Quantity squared. Close those parens, get out here and hit enter, and you see I get 1.305, and it keeps on going. 1.3, I will round to 2 decimal places, 1.31 is my new sigma W. Notice we could pick to build our portfolio any way we wanted. We could choose to have our portfolio designed where I didn't use half and half. I could have used 60% GE stock and 40% of the other. We could mix those around, and the more you pick from GE, the higher this number will go, because this is the bigger number. The more you pick from Oracle, the lower this overall number will go. But what I hope you notice is that 1.31 is definitely smaller than either of these two numbers separately. I haven't destroyed my risk. I still have a standard deviation of 1.31, but I can reduce it, definitely, by mixing them together. The next question in your mind should be, well, what if we bought 3 stocks? What would that do? Or 4? And the answer is, with the right stock mix, you can continue to reduce risk, and that can make you have a more stable portfolio. And you can choose exactly the level of risk you want and keep it that way for years, because if one gets too risky, you get rid of it and grab in something else to bring the balance back so that you can always keep it steady at 1.31 if you wanted to, or really any standard deviation that you were excited about. Not quite 0, but you get the idea. I think this pretty much wraps up probability distribution. We've talked about how to calculate expected value. We've talked about how to calculate these linear formulas and put them together and take old data and build it into new. And I think I'm going to let you go because I suspect that these kids are going to have a really loud shout in a little bit. And so I will see you next time. But until then, stay safe.